Good afternoon, everyone, and welcome to the Viessmann Academy. My name is Rob Waters, and on behalf of everyone here at Viessmann, we thank you for taking the time to join us today for our webinar on applications and piping strategies for condensing boilers. Today's seminar is the first in a series we're going to run on piping strategies and different ways to approach complex hydronic heating systems. Today's is an introduction seminar, and we will go through a lot of the fundamentals. And then as we move forward over the next months and so, we will get into more complex strategies and different types of applications. So again, thank you for joining us today, and we hope you enjoy our webinar. There is opportunity to ask questions. I'm joined today by my co-academy instructor, Mark Norris, and he will be answering questions if you post them in your GoToWebinar box on your screen. So feel free to ask questions, and Mark will try to handle those as we go through the webinar. So thanks and enjoy. So as I mentioned today, we are going to cover some fundamental stuff, and I'm going to start out with some sort of high-level objectives when you're putting together a design and you're thinking about what components I require and how you're going to tackle a hydronic heating system. So I want to make sure everyone always keeps in mind what are the objectives that you're trying to achieve, and I'll go through some of those. And then we'll have a review of some fundamental principles for hydronic heating, and hopefully give you the foundation you need to approach any sizing or troubleshooting problem with a hydronic heating system. Thirdly, we'll look into the control and piping strategies we use for condensing boilers and introduce you to some of the principles that are required with today's modern hydronic heating systems, and especially with the flow and temperature requirements of condensing boilers. Lastly, we'll wrap up today's seminar with a look at the new Vitodens 100 application guide, which was just launched last week by Viessmann, and it's a valuable resource now for contractors and distributors to put together designs that are tried and true and will work for a Viessmann hydronic heating system. So that's our topic for today, and hopefully you'll learn a lot in this 1 hour webinar. So the first thing I want to tackle is control objectives for hydronic systems, and look at sort of where we should all be thinking about when we're designing and sizing and selling hydronic heating systems. And this is kind of high level stuff, but it starts out with maximizing occupant comfort. We want to maintain a consistent air temperature, and we want to vary the temperatures as the occupants desire. Hydronic heating has the advantage over some other forms of heating that it almost by default has higher comfort levels. But if it's not done right, you can end up with temperature swings in the space. You can end up with too hot, too cold. So we want to always keep that in mind, that our control strategy and our system design should always keep that in first and foremost. We want to make our customers happy and comfortable. The second objective is to minimize energy consumption. We got to make sure that we maximize the condensing effect of that condensing boiler. We want to minimize the on-off cycling. It's the biggest thing that can rob you of efficiency and degrade the lifespan of a boiler, is by cycling it on and off. And again, especially with today's modern low-mass wall-mounted condensing boilers, you can cycle them to death if you're not careful. So we want to make sure we avoid that. The other thing to keep in mind with the system is we want to minimize the electrical consumption as well. We talk about saving the customer fuel on their gas bill by putting in a modern high efficiency boiler. But we also want to make sure that we're not creating a system that's got huge electrical consumption, because electricity is a very expensive energy source right now. So we want to keep that in mind as well. And then the last thing that our objective should be about is protecting the equipment. Again, we want to minimize that on-off cycling. We want to protect the radiant floor system from getting overheated. We want to make sure that everything's working in concert for a long service life that's going to not cause the customer any problems. So that's our objective, a comfortable, efficient system. But what are the challenges? And the challenges are huge, because we have heat loss and heat gain from our heating system, but we also have a lot of other things going on that make it hard to maintain that constant even temperature. We've got outdoor air temperature changes. We got solar gain. We got wind and infiltration losses. And then we add in there internal gains, people and equipment. So all of these things make it very challenging to meet our objectives. And again, if our control system is not responsive enough, if we're not getting room temperature feedback, if we're not looking at what's going on outside the building and we're not modulating water temperature the way we should, it can be very difficult to maintain that constant temperature. So the objectives are there for that efficient, comfortable system, but it's a challenge. And the other challenge that we're thrown at and more today is multi-function, multi-temperature requirements. If all I'm doing is hooking a boiler up and heating a concrete slab, it's a pretty simple dynamic. The control scenarios, it's quite easy to handle that. But more and more today, we're dealing with multiple temperatures. We need to staple up tubing under the wood floor, so that requires a higher water temperature than the tubing that's embedded in the slab. We need to look at a fan coil to provide the air heating requirements and the ventilation and the air conditioning and the humidification of the home. And then we throw in their domestic water requirements. And you can see you got some complex relationships going on here. We got to make sure that the boiler's doing what it needs to do to satisfy all those loads without cycling itself and without burning excessive amounts of fuel. And we want to keep the customer comfortable. You throw on top of that even more complex system, pool and spa heating and snow melting requirements, and it certainly are great benefits that you can provide your customer with a hydronic heating system. But again, it makes the challenge even more. And we're not going to tackle that part of the system. That'll be for future webinars, but we're certainly going to cover those multi-temperature heating systems today in our basic webinar. So that's sort of a high level. Let's think about how we can keep systems comfortable, efficient, and long-lasting. So I want to jump in now and view some hydronic fundamental principles. And it starts out with understanding the universal hydronics formula. And I don't want to overwhelm you with formulas and numbers and that, and that's not our objective here at all today. What I want to show you here is the relationships between these different parts of that formula that are very important to understand in how we control hydronic heating. And we find that a lot of contractors are new to the industry, don't have some of these fundamentals, and this is where they sometimes fall flat. So why is this formula important to understand? Well, it's really a few things. Sizing pipes, sizing pumps, sizing low loss headers, zone valves, any of the components in that system. They're all crucial to understanding the relationship between flow and temperature. If you understand this formula, it makes it a lot easier to do those things. The other thing is troubleshooting systems. Understanding the relationship between flow and temperature and BTU output is crucial to understanding why a zone is not getting the heat it needs, why it's getting too much heat. So it gives you the ability to really understand the dynamics of a system. And then the last thing is that controlling the heat transfer rate from any hydronic system is all about understanding flow and temperature. So let's look at that formula a little closer and show you what the elements are. It starts out with GPM. That's gallons per minute of flow rate. That's the fluid flow rate through the system. And it's really the crucial element delivering BTUs, because if you're trying to deliver a certain amount of BTUs to a space, you got to have the right flow rate. You don't have the flow, you won't be able to deliver the BTUs. Excessive flow can also be a problem, because then you can get velocity noise, and so too much or too little flow is always a problem, but it is crucial to delivering those BTUs. The heat loss at design of the area being heating, that's your BTU per hour. That's the energy that you're trying to deliver to the area. If you know that, everything in sizing a system starts with that, but now we have to deliver those BTUs. The delta T up here, that's the temperature drop across the system. And it's typically 10 or 20 degrees Fahrenheit in most hydronic systems, 10 degrees maybe for a radiant system. Most fan coils, radiators, cast iron baseboard are all going to be in that 20 degree range. So that's a crucial part of designing that, understanding that formula. And then the last variable in this equation is is kind of a mathematical formula which represents the specific heat properties of water. So it's 8.33 pounds per gallon times 60 minutes per hour times 1. And that gives you approximately 500. Now, one thing to consider is that if you're not using water as the heat transfer medium, then the specific heat is a little different. So this does change a little bit if you're using glycol water. But that's the fundamental formula, the universal hydronics formula, and it's one that's really important to kind of understand. And we'll move forward a little bit more here. The formula, as you see it, we can simplify that a lot. It starts out with understanding delta T. Most hydronic heating systems use a 20-degree temperature drop. So if it's a baseboard system at design condition, we're supplying 180 Fahrenheit and we're returning 160 to the boiler. So that's my 20-degree delta T. Now, if you look at do the math here, we can simplify this even further. So the GPM is equal to the BTU divided by 10,000. This becomes a very easy formula for people to remember, and it's one that's stuck in my mind ever since I started in the hydronic heating business because it's such a simple, easy thing to remember. If I need to know the GPM for a certain device, and for example here, if I got a 90,000 BTU boiler and I'm sizing a pump, well, it's very simple. 90,000 divided by 10,000, that's 9 GPM. So if I'm trying to figure out how much flow rate I need to a baseboard circuit, and I got a baseboard that serves an area of the upper floor that needs 30,000 BTUs per hour. So again, BTU divided by 10,000, that baseboard loop needs 3 GPM. You know, same thing, I got a radiant floor system in the basement, and the BTU loss for the basement is 40,000 BTUs, and I do the math, and bingo, I get 4 GPM for that area. So now you got to remember this is for water as the heat transfer media and a 20-degree delta T. So it is different if you change those variables. But as something to keep in your mind when you're sizing pipes and pumps, this is certainly a great thing to remember and to be aware of. So let's look at another aspect of that universal hydronics formula. Our objective is to control the rate of heat output into the building. And that's sort of, again, goes back to that control objective. How do I vary this part of the equation? Well, there's really only 2 ways to do that. I can vary the flow or I can vary the temperature. So this comes down to sort of the very fundamentals of what we're doing. We're controlling flow and we're controlling temperature. It used to be in the old days that our hydronic heating system was very simple. The boiler was kept hot all the time and we just turned the pump on and off with a thermostat. So it was a very simple, easy, basic relationship. Today, it's a little different. We have more complex things going on. We have modulating water temperatures going to the boiler, and we have different things going on. So if we look at the 2 things going on in a hydronic system now, it's flow control and it's water temperature control. Flow control being turning things on and off with zone valves or pump, or even balancing with a hydronic radiant floor system. And then the water temperature control is things like outdoor reset of the boiler, outdoor reset of the mixing valve, or even a thermostatic mixing device. So today it's a little more complex. We want to maximize the efficiency of the system. We think back to that objective. We want to modulate the condensing boiler as much as possible. We want to use outdoor reset, and we want to then fine tune it with zone control. So it's oftentimes a combination of these 2 different types of controls that we're working with. So let's look a little closer at outdoor reset. Why use it? To me, it's 2 things that you gain when you start modulating the water temperature in a hydronic heating system. It's comfort. You get more consistent, even temperatures, more constant heat output to match the load, and it's sort of keeping up to the heat load rather than catching up. So it's one of the number 1 things you can do to improve the comfort level for your occupants. The second thing the outdoor reset control really does is improve the efficiency. And especially with condensing appliances, we increase the amount of condensing, we eliminate overheating, and we get longer run times and lower standby losses. Those things all add up, and you harvest little pieces of efficiency all along the way to save your customer the maximum amount of fuel. So that's why we want to use it. How do we do it? Well, it's all based on the relationship between outdoor air temperature and the boiler or supply water temperature. Heat loss in a building is changing continuously, and it's always based on how cold it is outside. So if we can vary the water temperature according to how cold it is outside, we will get a match. The output of the boiler will match the heat loss of the building. That's the theory behind outdoor reset, and if it's done right, it really works well to provide that constant, even temperature in the space and the maximum efficiency of the boiler at all times. Everything on the outdoor reset is based on understanding the boiler outdoor reset curve. So this is a chart which is used to determine what setting you put in the boiler, because as an installer or a designer, you have to choose what heating curve you use for the building. Now, these are the heating curves along these different lines represent different heating curves. We find a lot of systems get installed and the installer never changes it from the factory default, which is 1.4. Well, that may or may not suit the requirements of the building. So It's boiler supply on this side, it's outdoor on the bottom, it's the heating curve you select over here. So if I select a heating curve of 1 on my control, this is the kind of water temperature profile I get based on the different temperatures outside. So if it's minus 20 outside, I'm delivering 140 Fahrenheit. If it's plus 10 outside, I'm only delivering 95. So this would match the requirements of a certain type of system. So understanding outdoor reset and setting it up correctly is really a big part of understanding and providing those objectives to the customer. When you're setting up a system, these are the basic parameters that we go through. We select a heating curve based on the type of distribution system we have. So you can see here on the top, C would represent high temperature heating systems. Fin tube radiation, fan coils typically operate up here. So you would select a heating curve of 1.6, for instance, for a fin tube radiation system. And that would deliver you, about 180 Fahrenheit on the coldest day of the year. If you've got a medium temperature heating system, cast iron radiation, staple up radiant floor systems, they need lower temperatures, so I get lower heating curve. And then again, the very low end of the scale is my high mass concrete radiant floor systems, and that's where I get the very low heating curves, 0.6, 0.8. Now, for those of you who live in colder parts of the country, the heating curve does not stop at minus 20. It continues on all the way over to minus 40. These curves carry on. This particular chart doesn't show that. A lot of our manuals do show that. So it's very important that you not only have the right design and components in your heating system, but that the people who are setting it up understand where to make these settings, because you can have the best design in the world, but if the guy who sets the heating curves doesn't understand that, you're going to defeat the objectives. If you have the wrong heating curve setting, the system will not be as efficient as it needs to be, and the customers will not be as comfortable because you'll get overheating. So just be aware of that when you're setting it up. And we're certainly available here at Viessmann to help you if you need to understand how to set up a heating curve. We can help you out. So those are some of the foundational pieces of information that I think it's important for everyone to understand before we jump in and start tackling design and strategy. Understanding the relationship between flow and temperature, understanding the relationship between the temperature drop and understanding outdoor reset controls and the difference between water temperature control and zone control. So hopefully we'll take that information now and move forward and start thinking about, okay, how do I design a system and what do I need to take into consideration once I've done my heat loss assessment. I know I got a house that needs 100,000 BTUs of energy. I've selected my what kind of boiler do I pick? What kind of components do I pick? So let's move forward and tackle some of those questions. So before I start designing and sizing a system, there's a few, again, basic things I need to consider. It starts out with what are the water temperature requirements for the different parts of my system. Every heat emitter has different temperature requirements, and we have to decide what is required for each one of those, and we'll look a little more closely at that in a minute. What are the boiler requirements? There's different types of boilers out there, low mass boilers, high mass boilers. They have different requirements for flow and temperature, and we always want to make sure that we maximize the condensing efficiency of that boiler. So we're focusing here primarily today on condensing equipment, but there may be some different questions you ask if you're using maybe a non-condensing boiler, which is not as common today, but certainly there is still non-condensing boilers out there. They have different dynamics. They have different requirements for temperature and flow and things like that. And then the third variable that we need to understand and ask the questions to the customer about before I start is, what are the zoning requirements? So you need to ask your customer what their expectations are for having areas with different use patterns, or are they going to use night temperature setback? I need to look at those areas that are going to experience solar gain and internal gains and address my zone control to make sure I take that into consideration. So those are the three kind of fundamental things I need to understand before I can tackle any system is, what does the system components require? What does the boiler require? And what do the individual zone and occupant requirements for that building? And there's a million different combinations and permeations of these three variables. So that's one thing with a hydronic heating system is you're able to really fine tune a system to the customer's requirement, but there's a lot of different combinations of permeations and everyone's different. There's going to be a lot of variables, and you can offer your customer something that they maybe can't get with just a basic forced air system with one thermostat in the whole house. We can really fine tune the comfort for every zone of that building, and that's an advantage of hydronic heating. So let's look at the typical water temperature requirements for different types of heat emitters. There is some generalities here, but we've tried to group them together into the requirements based on temperature. So it starts out with high temperature emitters. Fin tube radiators are probably the highest temperature because they're against a low mass, small copper and aluminum fin tubes that require fairly high temperatures. Fan coils require pretty high temperatures in most cases as well. Pool and spa heat exchangers and domestic water production. Those are all things that require the boiler to drive to a fairly high temperature at times to satisfy the requirements of those devices. Now, I'm showing a range of temperatures here because there is a variety of ways you can design a system. Like if I put in longer lengths of baseboard in the building, I can get away with lower water temperatures. If I put in a bigger fan coil with more fins in there, I can get away with lower water temperatures. So these temperatures by no means are absolute. You have to delve deeper into how the system was designed, but these give you some ideas. The medium temperature emitters tend to be those cast iron radiators and the radiant floor systems that are stapled up under the floor. Those tend to be in that 100, 110 up to about 150 Fahrenheit range. Cast iron radiators require a lot lower water temperature than fin tube radiators because there's a lot more mass. They tend to hold the heat better. There's more surface area. So they can really work well with condensing boilers because you take an old home with cast iron radiators and you put a condensing boiler in there, it's a perfect match because you get excellent performance in that condensing boiler. You can run fairly low water temperatures through those rads. And if you take control of the water temperature in that old building, you'll improve the comfort level for the occupants tremendously because a lot of those old homes with cast iron rads, they maybe had one thermostat in the whole house and they had a high temperature boiler in the basement. So that was not a great combination because you tended to overheat certain areas. It was either too hot or the rads were either smoking hot and you're opening the windows because it was so hot, or you didn't have enough heat. So the ability to use outdoor reset control, modulate the water temperature to a cast iron rad, give it high temperature when it needs it in the cold times of the year, but modulate the water temperature down in the spring and the fall, you will really meet those objectives of more comfort and more efficiency for your occupants. So the low temperature emitters, that's your high mass radiant floor. Concrete floor would be certainly the shining star of low temperature emitters, and that it allows you to run very low water temperatures, 80, 90, 100 Fahrenheit most of the time in a radiant floor system. That's where you can really drive the efficiency to the max on a condensing boiler. Now, the challenge becomes, as I mentioned earlier, what if I have a high temperature emitter and a low temperature emitter on the same job? How do I run the boiler at two different temperatures? Well, this is where we need to get into looking at breaking that system up into different circuits that get different water temperatures, and we'll show you how to do that in a minute. Let's look at the boiler requirements in relating to temperature. How do I maximize the efficiency of a condensing boiler? These two boilers both have an AFUE rating of 95%. Does that mean they always run at 95%? Well, no, they don't. Efficiency of a condensing boiler is based on return water temperature to the boiler. That 95% rating of the boiler is based on a specific test that was done in a laboratory with a fixed set of conditions. You take that boiler out in the real world, the story is very different. Because in the real world, do I hook it up to a radiator? Do I hook it up to a floor heating system? Do I hook it up to a fan coil? All of those things, as you just saw, require different water temperatures. So the delta T across the heating systems can be very different for a cast iron radiator or a fan coil system or a high mass radiant floor system. So the efficiency of that condensing boiler is going to range between about 85 and about 98%. And it all depends on how often you get below that dew point. The dew point of natural gas is the key point here because at about 130 Fahrenheit, you start condensing the moisture out of the flue gases. So that's the critical point in a condensing boiler. As soon as you get that water temperature coming back to the boiler below 130 Fahrenheit, you're going to get condensate coming out of that boiler. And that's when you get that boost in efficiency up into the mid 90s and higher. And again, this chart's not absolutely 100% for every product, but it certainly shows you the relationship and how we want to always think about it in our design. Let's get the coldest water temperature coming back to that boiler as possible. And if you're running that boiler hot all the time, it's not going to condense and it's not going to get the efficiency. We've seen lots and lots of systems where we've gone in to troubleshoot and we look at the way the boiler's laid out, and the boiler's running hot all the time. So even though he's got a condensing boiler in there, and you got people running a hot loop on the condensing boiler, that never sees cold temperatures. So we got to really make sure we meet our objective of providing the most efficient system as possible, and that means how do I get the coldest return water coming back to the boiler? There's also some constructional requirements of the boiler we have to take into consideration. And this is to do with the mass and water content of the boiler. Typically, our wall-mounted series of condensing boilers, that's the Vitodens 100 and 200 series, these fall in the category of low-mass heat exchanger construction. They have low water content, and they require minimum and maximum flow because of the structure of that heat exchanger. They have higher friction loss, so that affects your pump sizing and how I want to pipe up the system. And there may even be temperature limitations on some of these. So that product has certain constructional features that really determine how I'm going to use that. You compare that in contrast to our Vitocrossal 300 series of boiler. That's a high mass boiler with lots of water content and no minimum flow requirements. It's got low friction loss through the heat exchanger and high water temperature capabilities. So right off the bat, you can see that these boilers are very different animals. They're both high efficiency condensing gas boilers, but they really have different dynamics. That low mass construction requires that I get the BTUs out of that boiler right away, or the thing's going to cycle off on high limit. If I'm not getting the right flow through that heat exchanger, it's going to overheat and shut down on limit very rapidly. And that's what leads to short cycling, is when you have a mismatch with flow and burner firing and the thing short cycles. So in contrast, on the bottom here, the high mass and high water content of that Vitocrossal, it makes it almost impossible to short cycle that boiler because it's got so much mass and you get a flywheel effect inside. It just doesn't tend to short cycle at all. If you put a Vitodens 100 or 200 in the right situation and control it the right way, it doesn't short cycle either. So it really is important to recognize those two features and design my system accordingly. So let's look at the piping requirements for those different types of appliances. That 100, 200 series, you must maintain flow through the heat exchanger while the burner is firing, or you're going to have problems with short cycling. So we typically require a dedicated boiler pump on that low mass boiler, and we like to see a piping configuration of primary secondary with either closely spaced tees or a low loss header. Now I'm going to elaborate on both of those, that primary secondary piping in a minute, but it is very important to recognize that because of the way that boiler is constructed and designed, you have to do certain things with flow and piping and having the right pump capacity. You contrast that again to a high mass boiler, the Vitocrossal 300. It's not flow sensitive. It doesn't need a dedicated boiler pump, and we don't need to do primary secondary because it gives you that mass and water volume inside the vessel. I can actually run that boiler with no flow, and it'll eventually shut off on limit, but it's not going to be in 5-10 seconds like it would be for the low mass boiler. So it's a very different animal, and it has very different requirements in how we can pipe it up. And basically, if you look at the fundamentals, it comes down like this. The low mass boiler with the high friction loss typically needs to be piped up with primary secondary piping. And now there is exceptions to this, and I'm not saying everything has to be piped up like this, but in general, to meet those objectives of protecting the boiler and maximizing the efficiency and keeping the flow in the as we require through that boiler heat exchanger, we generally want to use a primary secondary configuration. In contrast with the Vitocrossal 300, pipe it directly to the system. Have the pump push the fluid right through the boiler. The friction loss in that boiler is very low. It's got the mass and water volume that it can handle fluctuations in zones opening and closing without driving the boiler crazy. So you'll see very different piping scenarios with a low mass boiler versus a high mass boiler. So I want to focus a little bit more on primary-secondary piping. It's called hydraulic separation is what you're doing with a primary-secondary piping configuration. And we show two different ways of doing this here. Option 1, closely spaced tees. Option 2, low loss header. Now, which one do I use? Is there any differences between those two? Well, fundamentally, they provide exactly the same hydraulic separation of the primary and secondary circuit. So you can choose either one of those. We are big proponents here at Viessmann of the low loss header, and I think it's the best way to provide that primary secondary piping without driving yourself crazy about figuring out how the piping connection should be made and saving yourself a lot of time and labor and grief on the job site. So we tend to show primary secondary with low loss headers in most of our drawings, but just recognize that for anywhere we show a low loss header, you can use closely spaced tees as well, and they'll provide the same hydraulic benefit. There is some rules to closely spaced tees, like they should be no more than 4 pipe diameters apart, and you want to have a certain length of straight pipe before and after the closely spaced tees. So there is some sort of basic ground rules you have to follow if you're going to pipe up your own primary secondary system with closely spaced tees. So that's again another reason why I like the low loss header, because it kind of takes that out of the equation. You really can't make a mistake with a low loss header. It's going to give you that exact separation that you require. So let's take a closer look at how it actually works. The low loss header and the primary secondary separation. We have on the primary side of that low loss header, we have the primary loop. And this is through the boiler and through the low loss header. So the pump on that side of the low loss header, on the primary side, only has to overcome the friction loss of the boiler and the primary loop piping. Now on the secondary side of the system, you have another pump which is providing the flow required through the emitters, whether it be a fan coil or floor heating, whatever. That pump only has to overcome the friction loss of the secondary side of that system, the secondary piping and the heat emitters on that side. So in this way, the two circuits are hydraulically separated. They both have flow. The flow can mix between those. Now this little graphic here doesn't show them mixing, but they do mix, and I'll show you that in another slide. But what we're doing is, again, we're hydraulically separating the fluids so that each pump only has to look at each part of the system. And the benefit to this is that the primary loop's happy and the secondary loop's happy. We can have things changing on either side of that loop, and it won't drive the system crazy, because the boiler will react to changes in the zone control whereby it'll see the flow reduce on that secondary side. So the net result is, from our perspective here at Viessmann, the biggest benefit of that primary secondary separation with a low loss header is a happy boiler. We like happy boilers. Sad boilers, they don't last as long. They tend to burn more fuel. There's wear and tear in the components if you're short cycling them. So by always getting the flow it needs, that boiler is less likely to short cycle, and it's less affected by zones that are going on and off, and you get micro loads in the secondary side and things like that. So that is definitely our objective here, is to keep that boiler happy. And if it's done right, works perfect. Let's look a little closer inside that low loss header. The previous graphic just showed the flow being completely separated, but in reality, what happens is, depending whether there's more flow on the primary side or more flow on the secondary side, you get a little bit of a mixing action within that low loss header. So if you look at this one on the left here, we have a higher flow on the primary side than the secondary side. And that could be because there's maybe only 1 or 2 zones that are calling on the secondary side. So half the flow is shut off. So now we got a little bypassing action. The net result is the flow on the primary side stays the same. Look what happens if the flow is greater on the secondary side. Now let's have a scenario where all the zones are open, everything's calling for heat. The flow is still the same on the primary side. You get a little mixing action inside here from the secondary side. So now you're not trying to push all that flow through that boiler heat exchanger, which has high friction losses. So again, all the boiler pump has to do on the primary side is keep the boiler happy. and all the pumps and zone controls on the secondary side has to do is look after the secondary side. So in this way, we get that hydraulic separation, but still with some mixing. Now, one of the things we do with Viessmann boiler controls is we put a sensor in the low loss, the top of the low loss header. And it's typically located right at the top point of the low loss header here. That's typically on our Vitodens 200 series boiler. And that gives us a very precise control of everything that goes on in that system. So that's definitely a benefit of using that Vitodens 200 series boiler. So the third part of that control strategy starting point I mentioned earlier was to look at the zoning requirements. And I want to throw out a few ideas here for zonings. There's a couple different ways to tackle multiple zones to satisfy the requirements of different areas that require different temperatures or different control. One is by using multiple zone pumps, where you have a dedicated pump for each zone of that building. You can now have like a 3-speed circulator that you can use the speed control to vary the flow requirements for each area. It's sometimes hard to get exactly the flow you need for each circuit. So sometimes you may have too much or too little flow, and that's one of the downfalls of this is it's a little hard to get exactly the flow you require unless you're using a variable speed pump in each one of those circuits, which is certainly a possibility. And you also will tend to have a little higher electrical consumption than some of the other options I'll show you here, but certainly is something that a lot of contractors are really comfortable with. They use a multi-zone control module here to tie together all the thermostats and all the outputs and probably tie back and switch connection enable circuit back to the boiler. We're just showing just the zone control part of the system here. Let's look at another option, which is use a single pump and multiple zone valves. This is an option that generally lowers the electrical consumption. It gives you the ability to have very fine-tuning control with individual thermostatically controlled zone valves, because you can have power heads on a multi-zone radiant floor manifold, or you can use individual zone valves in each individual circuit. But it really gives you a lot of versatility to really get micro zones in each part of that building. And if you use a single pump with multiple zones that are opening and closing based on demand, you have to balance the flow. And one of the easiest ways to do that is, or one of the two ways to do that is to have a single speed pump and have a pressure bypass valve. A pressure bypass valve is a device that will bypass some of the flow when some of these zones close off. So if I have 3 zones closed and only 1 open, then 1/4 of the flow is going into the zone that's open and the rest is bypassing. So the pump doesn't get overly stressed or higher electrical consumption. Now, today's days, you're seeing more of this, which is that same concept, but using a variable speed pump. And the variable speed pump now will react to either pressure, difference in pressure or difference in temperature, and will automatically vary its speed. So that's certainly probably the future of hydronic heating, is with these variable speed smart pumps that react to different changes in pressure. And so if a zone starts or 2 starts closing off, then that pump will just ramp down automatically based on the load on profile on the pump. So we may use a different combination of zoning strategies, but those are some of the things to think about when you're putting together your zoning for the house. So based on those 3 basic foundations, we can start designing the system. Let's say we have a system now with a fan coil circuit for the upper floor, and I got radiant floor in the basement. I know what my water temperature requirements are, and I can now start putting together my package. I've decided what boiler I'm going to use. I've picked the size required to meet the load, and now I can pick a piping strategy that meets the construction requirements of that boiler. And then I can look at the zoning demands of the building. I've met with the customer. They want to have protection against overheating in some areas. They want to have different temperatures in the basement than the upper floor. So you can break down how many zones you want to give them to satisfy their requirements. So now we can start laying things out. This brings us to the 4th part of our webinar, which is an introduction to the Vitodens 100 application guide. Hopefully with all that foundational information there now, we can sort of move forward now and start to say, okay, what do I need for my application? So what this application guide is all about, the first module we've put together is just been launched. And it basically gives the installer or designer assistance with component selection, different piping layouts. It gives you wiring information. It gives you control information. It gives you design tips. So it's really a great reference guide or resource for the contractor and distributor to be able to look through this book and say, okay, that's what I have. I have a high temperature circuit, a low temperature circuit, and a Vitodens boiler. And now I can pick a piping layout, and it shows you all the components that are required. This is only the first module of this application guide. We are coming out with other modules for the Vitodens 200 and the Vitodens 222F, and probably in the future other boilers as well. Now, we also have piping information in our technical data manuals and our installation manuals, so this is not the only thing, but we've tried to lay this out so it's a little easier to use. First thing in that book is just some nomenclature on how to recognize the different model numbers with our different boilers, like what the heck does B2HA mean? Well, that shows you what that's all about. We go into recommended applications. We talk about, radiant floor heating. What's the best boiler for that application? We have sort of suggested boilers and products to use for different types of applications. And then we've got a list of components. So when you go through the piping layout drawings in this book, you'll see all these components shown. So you can see, well, I'm putting together a design. Okay, I need an air separator. I need some zone valves. I need some isolation valves. It shows you where all those devices are. So you can actually use this book to put together a material list of products. And then we have piping layout drawings, and I'll go through some of these in detail in a few minutes, but those are the basic piping layouts that show you with some design notes in the bottom here, so you can see what's required to satisfy that particular layout. Then you have a control wiring diagram, and it shows you all of the wiring internal to the Viessmann product, but also if you have a multi-zone module, for instance, it shows you how we interface with that, with thermostats and zone valves and things like that. So it really gives you a real fast, easy, simple way to help you to design and lay out a system. The next step in that application guide would be control programming and setup. So we show you what the dials should be set at, how to set the heating curves, how to set the temperature for different parts of that system. So for the WB1B series, it's a fairly basic boiler, so there's not a real complex control. When you get into the 200 series boiler, it's going to be more complex because now you're into coding addresses and things like that. And we will show you what codes to use for each part of that system. So let's look at the different applications in this application guide. It starts out with number one, which is a basic one temperature system. And this is where it really couldn't get any easier. It's not a very complex relationship because for this boiler and for a single temperature system, it's just a low loss header or a primary secondary piping, and you've got a single pump feeding right into our load. So that's pretty straightforward. Again, if it's all you're doing is just a one temperature zone, it really doesn't get that complex. Let's move on to what's more common and what opens up more questions, which is the multi-temperature, multi-load application. And this is an application number 2 here where we're showing domestic water heating, fan coil heating, and floor heating. So this is a multi-temperature space heating system and domestic water production as well. So we show a low loss header separating the boiler circuit from the heating circuits. Now we do show the domestic water tank being piped off of the primary circuit of the boiler. I'm going to show you in a few other applications. We also show a drawing which has the domestic water tank piped off the secondary side of the system. And I'll talk about that, the pros and cons of doing either one of those in a few minutes. But for now, the drawings were showing the primary loop being directly connected to the domestic water storage tank. Now there is 2 pumps on the primary side of the system now. P1 is the boiler loop, the primary loop pump, and P2 is the domestic water generation pump. They're both piped in parallel off of that primary loop so that we can prioritize the production of domestic hot water. So the general rule of thumb with this is that when the domestic tank requires energy, P1 shuts off, P2 comes on, and the boiler will ramp up to a higher temperature. That allows us to provide very quick, fast recovery of the domestic water tank. When the domestic water tank is satisfied, P2 shuts off, P1 comes back on, and the boiler will drop down to a lower temperature based on its outdoor reset setting. and that's going to satisfy your space heating loads. So that's the basic fundamental of domestic water priority. The advantage of having domestic water priority is that you can get very fast recovery of the tank, and you don't have to add a lot of extra BTUs to the boiler size to satisfy domestic hot water. So your boiler's not oversized for the space heating loads. Now, on the secondary side of the system, you have a 2-temperature heating system. So how do I provide a water temperature I need to satisfy the fan coil and a lower temperature to satisfy the radiant floor system? And this is where our mixing device comes in. So here we're showing just a basic 3-way thermostatic mixing device. So we may have the boiler producing, say, 150 Fahrenheit water, which goes right into the fan coil, but that water temperature is taken and mixed down before it goes into the radiant floor system. So that thermostatic valve, we can set that to whatever. This is a 1 temperature set point device, so I may set that at, say, 110 Fahrenheit. So that even though the fan coil gets a higher temperature, the boiler is generating a higher temperature, but I'm protecting the floor from overheating, and I'm giving the floor the temperature it needs to satisfy its requirements. So that's a very common multi-temperature, multi-function heating system, and we show you in this drawing how to pull that all together. And of course, there's other parts to that application guide, because we'll also show you all the wiring requirements. We'll also show you all the control programming requirements as well. So I'm just going through the piping layouts today because we don't have time to go through all those other things. Let's move on. Application number 3 is the same basic fundamental idea, except for now we're using the Vitodens 100 with the Combi Plus instantaneous domestic water generation device. So this allows instantaneous domestic water production off of the Vitodens boiler, and then separate tappings to feed into the low loss header, and I got a multi-temperature space heating system over here. So same dynamics, it's just that now inside that Combi Plus unit is a plate heat exchanger, a pump, and a diverting valve. So now I get domestic water priority, because every time there's a flow switch in here, every time it sees flow, it's going to instantaneously flip over, isolate the boiler, create domestic hot water, and then flip back over to space heating when it's done. So you get domestic water priority on this one, absolutely, because it's going to divert the water flow away from that space heating system. This is an application number 4, which shows a multi-zone space heating system using a single pump and multiple zone valves. We will show you in the wiring diagram how to make that all interface together with all the zone control devices. We'll show a typical multi-zone control box here where all of your zone valves and pump and thermostats are all tied together, and then they feed back information to the boiler control. And then you have domestic water priority on the primary side of the low loss header, providing domestic water priority. Now, very similar but different on the secondary side is an application where we have the same thing happening over here on the primary side with domestic water prioritization, but on the secondary side we now have a multi-pump, multi-zone system. So again, the fundamentals are almost the same as application 4. It's just that when we show the wiring diagram on here, it'll be different because you'll have multiple pumps rather than one pump and multiple zone valves. The other thing on this secondary side of the system on the application 4, you may need to have a pressure activated bypass in here if you don't have an end switch to shut off that pump. If all the zones close, we make sure we don't deadhead the pump. So there may be a requirement there to add that in there as well. Application 6 is a multi-temperature heating system like we've talked about, but here we've added the domestic water production onto the secondary side of the low loss header. So there's pros and cons to this. One of the pros is that pump number 2 now does not have to overcome the friction loss of the boiler. So that pump will be a lot smaller. Typically the pumps on the primary side of the low loss header are bigger capacity pumps because they have to overcome the friction loss of the boiler itself, which in some cases can be quite high. So this now provides us with the ability to make that pump only have to overcome the friction loss of the coil and the secondary side. So it's a smaller pump. You also now have the ability to have the boiler providing heat to both the space heating circuits and the domestic water circuit simultaneously. So this is the opposite of domestic water priority. Now we try to satisfy all loads at the same time. And that can avoid situations where you have long periods of domestic water production and the space heating system actually starts to cool down. But the disadvantage of that is that you may not be able to heat the domestic water up as fast. So you really have to look at the dynamics of your system and say, and it also, may require that you upsize the boiler to meet that additional capacities with all loads running at the same time. The advantage of domestic water priority is that when you turn the boiler pump off and have all the full capacity of the boiler available for domestic water production, domestic water priority, you don't need to upsize the boiler to satisfy that. With this strategy here in application 6, you may have to consider upsizing the boiler to satisfy all these loads at the same time. And that can be a problem with sometimes oversizing the boiler for space heating when there's no domestic water call-in. Now you have a boiler that's oversized and maybe short cycling. So as you can see, there's pros and cons to having the domestic water on the primary or secondary side. My personal opinion is that having domestic water priority with the boiler on the primary side of the system is my preference, but there may be other people that would disagree and say, I want to have both loads running at the same time. So we do give you both options, and we sort of show you the reasons why we do that. Okay, so those are all the applications that are currently in the Vitodens 100 guide. I want to show you a couple other piping applications that are coming in phase 2 of the application guide, and that's with a Vitodens 200 boiler. You can see hydraulically here, everything is exactly the same as I've just talked to you about. Domestic water priority with 2 pumps on the primary side of the low loss header. I've got high temperature heating and low temperature heating. The big difference here now is with the Vitodens 200, I can now use a motorized mixing valve, which communicates directly to the boiler. And now I have full outdoor reset modulation on that lower temperature circuit. The advantage here now is I can have 2 heating curves, one for the high temperature load and now a separate heating curve for the low temperature load. This gives you much more precise control over that secondary side of the system. And in our opinion, it's one of the main reasons why you would want to use or consider using a Vitodens 200 boiler over a Vitodens 100. You get much more precise control of the heating system. The motorized mixing valve gives you much more precision than that simple, thermostatic mixing valve that we showed earlier. And the other advantage of the Vitodens 200 series boiler is I can get into multiple motorized mixing valves. So this is actually a 3 temperature system on the secondary side of that boiler. I've got 2 heating curves, one for each section of the radiant floor system, and I've got a separate heating curve for the high temperature circuit. So this would be heating circuit 1, heating circuit 2, heating circuit 3. And again, with 2 motorized mixing valves and a heating curve for the high temperature circuit, you get, again, ultimate precision of control. So this is the things you can get into when you start talking about how do I really improve the comfort and efficiency for my customer. You spend more money to get motorized mixing valves and a Vitodens 200, but the benefit is going to be a much more precise, comfortable, even temperature in that space. So it gets back to that objective I mentioned earlier, is if we want to provide our customer with precision of control, then this is the way to do it. Get into a more high-tech control system like you have on the Vitodens 200 series boiler. The other thing you can get into with certainly Vitodens 200 is multiple boilers. I can get into 2, 4, 6, even 8 boilers on that primary side of the circuit. So here, a lot of the fundamentals stay the same. Domestic water production, multi-temperature space heating, but now I can have multiple boilers feeding into that primary side of the circuit. So same principles, low loss header, but now I'll have a cascade control to modulate those boilers and stage them on and off to satisfy the load. So instead of one boiler doing that, I've now got multiple boilers. So we'll elaborate on some of these Vitodens 200 series piping layouts in our next series of webinars. And we'll also look more detail at some of the programming and setup for Vitodens 200s and also for things like snow melting and pool heating and things like that. So that's pretty much all the time we have for today. I really thank you for joining us and encourage you to look online at that application guide. It's available for download on our website. You can also contact your Viessmann sales rep or come to one of our seminars to learn more about a lot of these topics. But we certainly thank you for joining us and hope you've learned some of the basics and fundamentals and moving into more advanced theory of how to design and size and put together a hydronic heating system. And with our design guides, I think we make it easier for you now to pull together and pick the application that suits your requirements. So on behalf of myself and Mark Norris, we thank you for joining us today and encourage you to visit us again on one of our other webinars. The other thing to make note of is that all our webinars are now online and available for viewing at any time on our website. So check that out on the Viessmann Academy section of the website as well. Thanks for joining us, and signing off here from Waterloo, it's Rob Waters, and thank you again.